So we again use the same quantum principle itself to
Sir,
actually.
sorry to disturb. Sir, can you just a little bit raise your voice? Sir, your voice is very low.
Yeah, okay, okay.
Thank you.
So
Thanks.
okay, to do that, we have to use a quantum system itself to fight against these quantum computing things which can break, right? So we also use like how we are going to basic aim of this session will be how the quantum technology is going to break the current crypto system. We'll go in details, and also we are going to elaborate on how quantum technology are creating the unconditional secure, right? So we will also emphasize on the word called unconditional, why it is called unconditional. Okay, so if you take about any cryptography system, right? So you have a plain text, so you need to convert into form which cannot be understandable, right? So that we call it as a ciphertext. So how do we do it? We use a key to scramble my input data such a way that it became a ciphertext. Now, while I doing that, I should also remember that the system has to it will be the inverse process, right? If from the surface test with the key, I should be able to get also my plain text. So it should be a reversible process, right? Okay, so the key here, if you see here, the key is the main element, right? If the keys are sacrificed, then it is easy for somebody to decipher your data. Okay, so one of the classical, if you talk about what is one of the unconditional security is, for example, we call it as a one-time pad as a unconditional security. So when you talk about the security, right, we also want to know about what is called the informational security. For example, I want to so how much entropy. So it's all boiled together to a common thing called how much is the entropy of my keys, right? For example, how much easy it is to guess somebody the keys, or how easy to somebody to do some operation and get the keys. Also, when we talk about the information security, for example, I am having a one bit, and I am trying to encode that with one bit, and I'm transmitting. That means that there is only one bit of security, right? For example, there is a if I have a coin, which is always there is the head is there. If I tap the coin, always it is head comes, right? If such a coin is exists, then there is no surprising element. So if there is no surprising element, and if you take a probability and a surprising element, it is inverse, right? So if that means that coin always flips head, that means that there is a very high probability that I will get a head when I flip the coin. So that means that I have very low surprise. Right? I didn't get surprise because it's obvious it's going to be head. So if you take a surprise and if you take a probability, it it is inverse. It all the relationship. Um, but when we see if you see the surprise equal to one by probability, if you see the head number of head, if it is the same, then one by one probability of guessing the head is one. So if one by one is equal to again my output is one, that means that it doesn't justify my formula, right? So what I have to do is it is not just surprising is not just one by probability. It is nothing but log of one by p. This again justifies what is the Shannon entropy, right? It defines the formula of probability into log base 2 of 1 by p. So basically, it is tells that how difficult is your guess, right? Okay, now, so that means that if I have a 2-bit number, right? If I am encoding with one bit, imagine that there is one bit I'm encoding. That means that I am keeping the second bit. For example, I'm doing a repeating or I am inverting. You do any operation to the second bit. If you see the information, if you see the security is only for the one bit. If I get one bit properly, then obvious that the next bit can be guessed. That means that it is it's not it doesn't give you unconditional. It is not theoretically quantified to be unconditional secure. But imagine that if I have two bit input and if I have a two bit as the key, then my probability of guessing is two, because that means that I'm probability of guessing is two is unknown. That means that I'm not able to make a combination of that much number of message bits to get my output to be. So if in this case, right, if something like this is happening, then we call it as unconditional security. So one-time pad is also considered. So for one-time pad to happen, right, the message length and the key length should be equal, right? And you should use just one time your key as read. Because why one time? Because it is a commutative operation, right? For example, and let's go to the so if okay, next not that. So if you go any operation, right? For example, if you take a encryption message, right? What you have in your encryption message, you have a message, you have a key, and you make a cipher, right? What will be in your decryption message? Decryption message, you have a cipher, you have a key, and you will get a message. So in the decryption function, if you keep the cipher and if you put the encryption system or when you overlap the encryption system, that means that you have a, for example, you have a, you want to get the message. That means that you both the keys are same. Then what I can do is since both the K and K are same, I can make a XOR of that. That means that I will left over is only the message. That means that these are commutative operation, right? So that means that I have to use this operation only one time. The information, if the OTP, the security, it is valid only when I say use my keys one time, and if it is in the same length of the key, then it is considered to be secure. But this is having a lot of problems. So as we go forward, we will see what is the other problems and how the quantum cryptographies are benefiting with this one and how they are using it. Okay, so let me ask Sashank to take it from here.
Sure, sure. So I'll just share my screen in a moment. This random number play a role in ensuring that we achieve the privacy using the cryptography. So Rajesh sir talked about the unconditional security that is offered by the OTP, which are one-time pad, and there the take home message is that the message length should be equals to the key length, because that only then the condition of uh, IID is satisfied, which is identical independent distributed random variables. So just in order to give a brief idea how it is unconditional secure, this can be seen from this simple theorem, which says that if we have a ciphertext and we want to guess the probability, guessing probability of the message or X bit of the message, then the ciphertext should not be helpful, which means that the probability of guessing the message with ciphertext or without ciphertext should be same. So in the proof is straightforward. Here, first we break down the conditional probability of guessing the message when the ciphertext is known, which is the joint probability of having the message and the ciphertext divided by the probability of the ciphertext. Now I'm claiming that the ciphertext is created through a random n-bit random numbers. And since these are random numbers, the probability of guessing any particular ith bit will be just proportional to the length of, 2 raised to the power minus n. N is the length of the bit, right? Because each bit is equally probable. So for the n-bit random number, this will be the probability. So then it is straightforward. Probability of guessing the message together with the probability of having the ciphertext divided by the probability of having the ciphertext will boils down to the probability of guessing the message multiplied by 2 raised to the power minus n divided by 2 raised to the power n. So ultimately we'll get that even if the ciphertext is known, the probability of guessing the message is equals to the probability of guessing message. And this is what we meant by the unconditional security, right? So one time pad ensures the unconditional security provided the message length is equals to the key length. And second thing is that the key should be truly random. And in the classical word, this truly ensuring this truly random is a hard thing to do. And if we are generating random numbers using mathematical algorithm, then it is, and at the end of the day, it is deterministic, right? So these are few of the challenges that we are trying to solve. But before that, let's talk about what is ideal security. So by ideal security, we want to ensure this Kirchhoff principle of cryptography, which says that crypto system should be secure even if everything about the system is known except the key. So in layman language, because in public key cryptography, everyone knows about the algorithm, right? We cannot hide the algorithm. So everything about the algorithm is known. So the security relies only on the key. If key is unknown, we can ensure that we have to ensure that the security of the crypto system is intact. And in order to have a good security, as I have mentioned, that keys should be truly random. And by truly random, I means that keys should be unpredictable and keys should be uniform. And if these two properties are ensured, then in statistical language, it boils down to having a IID source of random numbers. And so this is up to classical picture. But in order to have ideal security, what I want is that keys should not be copied, because at the end of the day, if Eve managed to copy the keys, then or there is a redundancy in the ciphertext, then it will not ensure the ideal security. And what if we can ensure that if there is a key tampering, we manage to detect it? So the last two features, that keys should not be copied, which boils down to having a no cloning theorem in the quantum mechanics, and key tampering should be detectable, which boils down to the collapse of the superposition when we measure it, right? So these two features are offered by quantum mechanical principles, and the idea to ensure that keys are unpredictable and uniform. This also is the essential features of the quantum mechanics, which says that the inherent features of the quantum mechanics is based on probabilistic structure and which is inherently random. So we'll see how we can achieve ideal security using the principle of quantum mechanics, and obviously we'll be taking advantage of the unconditional security that is offered by the OTP and correcting the pseudo randomness that is in the classical world with the true random numbers in the quantum world. So moving forward, before directly jumping into the quantum cryptography, we have to motivate ourselves and we have to understand what is the crux of the problem in the current classical crypto structure. For that purpose, I will briefly review this RSA algorithm, which guarantees the encryption mechanism in the data that is flowing through the internet. So RSA security relies on one-way function, which is the problem to factorize a very large number. So why it is one-way function? Because if the factors are known, multiplication is a simple problem, but finding out the factorization is a hard problem. So in order to generate the keys, the public key and the private key, we need to take two prime numbers, which are very large prime numbers, P and Q. There is no common divisor between P and Q. And we will calculate a function phi n, which is P minus 1 times Q minus 1. Then in order to generate the public key and private key, we have to further find out the greatest common divisor between phi n and the integer e, which is any arbitrary integer in between 1 and phi n. And we have to calculate d, which has the probability that d multiplied by e taken mod with phi n ensures that it is equals to 1, which means that de does not share any factors with phi. Then the public key will be created from the set of e and the large number n, and private key is generated from the set d and large number n. Then the encryption and decryption is straightforward, so I will not go into it. But the takeaway idea is that the RSA security relies on the one-way function, which is in the classical computational mechanism. It is a hard problem because the best known algorithm that we'll talk about is the number sheaf algorithm, and there also the resource and the time requirements are in exponential order with each increase in the bit length. But same is not true in the quantum world, right? So let's see the complexity or the security of the RSA algorithm. So in the y-axis, you can see that the number of operations are mentioned, which starts from 10 raised to the power 0 to 5 to 10, 15, and so on. And in the x-axis, we have number of digits d. And this vertical dashed line, which corresponds to 230 digits, is the highest number of digits that a classical supercomputer managed to factorize in a feasible amount of operations. And here blue curve signifies the increase in the number of operations as we increase the number of digits, and the red plot shows same in the classical world, as the number of digits are increasing, how the number of operations will go on. So complexity in the classical world is exponential n raised to power 1 by 3 log n raised to power 2 by 3. But in the quantum world, it is log n log n, which is in approximated languages d cube, which is third order polynomial in quantum world. So this complexity in the classical world corresponds to the number sheaf algorithm. And based on the current studies, the estimation says that RSA 4096 with 8194 logical qubits will be broken down in 229 hours, and Diffie-Hellman 521 bits will be broken down in 55 hours with 4719 logical qubits. And this is the alarming situation, right? Because the progress in quantum computational power is, the growth that we observe is exponential in order, and once a large scale quantum computer will be there, then increasing the key length of RSA or Diffie-Hellman or elliptic curve cryptography won't be of much help. So there should be a paradigm shift from the classical crypto structure to the quantum crypto structure that will move forward. So as mentioned in this particular slide, that the complexity in the quantum world is d cube, and this complexity is calculated using this Shor's algorithm. So, so in order to move forward to the Shor's algorithm, the idea is that there are algorithms in using quantum resources which are there at present, which will dilute the mathematical hardness of the problem in which our crypto structure is based. So algorithms are known right away. What is not there is a large scale quantum computer with logical qubits. So we have to tackle the error correction in the quantum computation technology. But the algorithm is known right away, and once a large scale quantum computer is there, the mathematical hardness will boils down to will boils down to the polynomial scale, and then increasing the key length won't help. So one particular quantum algorithm which will break down RSA, which will break down Diffie-Hellman, and some alteration of it will also be useful along with Grover's algorithm for breaking down the ECC, which is elliptic curve cryptography. So thanks to Shor's, who provided this Shor's algorithm, where he has intelligently used the relationship between the period finding problem and the factorization problem. So ultimately Shor's algorithm is a period finding problem, and once the period are known, then the factors of the large numbers are. So we'll talk about it in detail. And the idea is in the Shor's algorithm we use quantum superposition, and whenever there is a superposition of a state and we perform the measurement, then the final state that we get is a eigenvalue state corresponding to so there could be degenerate eigenstate corresponding to the eigenvalue, and so the end state is the superposition of all those eigenstates. And once we have a superposition of eigenstates which are separated by the period of the numbers that we are interested in, so using the inverse Fourier transformation we can determine the period. So that's the beauty of the Shor's algorithm. So in this circuit we have elaborated it properly. So there are mainly 3 stages in the Shor's algorithm. First is the creation of the superposition state, making a random guess, and then performing this controlled modular exponentiation operation in order to create the eigen state corresponding to the period order finding problem. And after performing the measurement, we'll perform the inverse quantum Fourier transformation in the superposed eigenstate in order to determine the factors. So I will elaborate how this unitary modular exponentiation contains the period R that we are interested in. So there is a lot more intricacies in the Shor's algorithm, but for covering the entire quantum cryptography, the takeaway message is, if we have a quantum superposition, we will create an eigenstate which contains the order that we are interested in, and once the order is determined, we can determine the factors using simple Euler algorithm. So 4 stages of Shor's algorithm are: first we have to make a random guess x within the range 1 to n minus 1. We have to ensure that there is no common divisor between x and the large number n that we want to factorize. Then using order finding algorithm, we will determine x with mod n, which we denote by r. So R is the order that we are interested in. If R is even, then x raised to the power R by 2 mod n will not be equals to plus or minus 1. So then we compute the greatest common divisor of x raised to the power R by 2 minus 1 with n, and x raised to the power R by 2 plus 1 with n. And once these greatest common divisors are known, then we can just by multiplying, we can see that these are indeed the factors of the large number that we want to factorize. This algorithm will not work if the order that we compute with the random guess x is an odd number, and in sometimes what could happen that the computed factors itself contains the factors of some integer multiplied by the large number that we want to factorize. So ultimately, it will contain the shared factors between the large number and the one and some integer m, and we won't be calculating the factors at the first place. But what we can do is we can start with some different x and estimate ensures that at least 1 by 3 times the Shor's algorithm guarantees factors. So this is the power of the Shor's algorithm. So now the last slide, in order to stress or motivate us about the limitation of the classical cryptography. So in the one-time pad screen, we have shared that Alice and Bob, the two trusted parties that want to ensure privacy in the communication that they are pursuing, they first create a ciphertext using some encryption key and the plain text, and send the ciphertext through a classical communication channel, which could be wireless channel, or it could be like the optical fiber. They're sending the data continuously. At the Bob end, Bob is having the decryption key, so it is decrypting the keys and ensuring that it receives the plain text. So there are two things that are involved. First, Alice and Bob has to have the same symmetric keys. So it involves a key distribution procedure, and the keys that they are sharing should be truly random. These are the two essential features. And if they are continuously changing the keys, then the attacker, and there is no redundancy involved, then it will be quite challenging for attacker to do crypto analysis and decrypt the cipher. But at the present scenario is that encryption and decryption is happening through RSA, which relies on the hardness of the large numbers factorization. So, so the smart Eve, which we call as Kevin, what they are doing at the moment, they are harvesting the ciphertext for the time being. And once there will be a large scale quantum computer, they will use that quantum computer in order to do crypto analysis and decrypt the message. Such kind of attacks are called harvest now and decrypt later. And as you might be familiar with, that there is a shelf life of all the data that we share using internet. Some of the data is extremely sensitive and it has a shelf life of 30 to 40 years. And it is the prime time to focus to ensure the security of such data, so that we can avoid this harvest now and decrypt later kind of attack. So we need to make a paradigm shift from the classical cryptography mechanism that we are using right now to the quantum cryptography, so that we can ensure that the smart Eve, which is Kevin, which is, even if it is harvesting the data now, even if the large scale quantum computer will be available, it will not be able to decrypt it, because quantum mechanical principle will not make it possible for the Kevin to do so. So in the recent year, multiple advancement has happened in the quantum uh, technology. People have managed to achieve the quantum advantages, and in some points, we can see that uh, there are some features which ensures the ideal security that we want to achieve, that we have talked about in the previous slides. And the in the experimental side, people have managed to perform the loophole free bell test. They have created random numbers using the superposition principle. People have developed the commercial QKD system, managing to share keys by breaking the 100-kilometer barrier in the optical fiber. In free space, advancement has happened. So, so it is the high time to discuss the quantum cryptographic principle, and fully motivated us, we can now jump into the quantum cryptography. So in order to ensure the security in the post-quantum world, there are two approaches. First is the quantum resistant approach, which relies on the mathematical algorithm. And another is the unconditional secure mechanism, where so the mathematical algorithm are safe at the present, and they are not, their security does not rely on the physical laws or the quantum principles. But the estimate is, or the assumption is, that such algorithms are hard even for the quantum computers to break down. So there are multiple algorithms. Some are based on lattice based approach, where the problem is to find the shortest vector in the lattice. Some are based on the code based. Some are based on the multivariate optimization problem. And on the other hand, the approaches which takes quanta particles in order to achieve the security, there the security relies on the quantum principle. They guarantee the unconditional security, and whatever the advancement in the algorithm, they are future proof. So this is the key distinguishing factor between the two approaches in the post quantum security. One is based on the mathematical hardness of the problem, that is even hard for the quantum computers, but it is the current assumptions, and it has not been proven for some of the algorithms. But on the other hand, using some physical properties, we can ensure the unconditional security. And there are, for the key distribution, there are trusted QKD, there are semi-device independent QKD, there are measurement device independent QKD, and there are also approaches for device independent QKD. And randomness is the added technology in this world. So let's first discuss about the post-quantum security based on the mathematical hard problem, which we are claiming that they are quantum resistance, but they do not offer unconditional security. So we are at this situation, which is the alarming situation. So current algorithms like RSA and Diffie-Hellman, they use mathematical hard problems, which are one-way function, be it factorization, be it discrete log problems, but using Shor's algorithm and the Grover, combined with the Grover's algorithm, either their security is boils down to polynomial time scale, or their security resiliency boils down to half the key. And estimates says that in the near term, the data that we are looking, whose shelf life is 30 to 40 years, in that time frame, it is projected that large scale quantum computer will definitely break down, and we need to ensure that harvest now and decrypt later attacks should not happen in such kind of data. So what we can do, we can go from the red circle to the yellow circle, and it is the present status where NIST is finalizing the post-quantum algorithms in order to move from the algorithm whose security has been proven that it won't be safe in the large scale quantum computer, to the algorithms which are based on another mathematical hard problems which are claimed that they will be hard for even quantum computers to break. So it is in the process of finalizing those, but even let it do the final estimate. But at present also, what we can do, we can use the available PQC, which are more advanced PQC, and they are in the final list or proposed final list. We can use those algorithms in order to encrypt the data and move from the yellow circle to the green circle, and that will be ensuring the quantum security in the post-quantum world, but in the using mathematical hard problem. But major advantage of using this post-quantum algorithm is the crypto agility that they offer. You do not have to create the entire different crypto structure, and so it will be cost effective. But if you want to ensure the unconditional security, then QKT is the way forward. So now let's briefly discuss about the quantum principle, which are ensuring the unconditional security, right? So as talked in the previous slides, in order to ensure the ideal security, what we want is, if there is a eavesdropping, we should be able to detect it, and there should be a way in order to avoid the cloning of the encryption keys. So let's see how quantum mechanics offers these two features. So first thing is the uncertainty principle in action, which in our school days we have done using this double slit experiment multiple times, where we have a source of the quantum particles. In most cases, it is the light source that we use, that is coming from a laser, in order to have a good coherence time, and the or what we can do is to have the electrons that are coming one at a time, and we pass such quantum particles through the two slits, and what we'll observe is that when there is no eavesdropper in the picture, then there is a superposition pattern that is formed in the screen, and we'll see the superposition pattern in the screen. But if there is a eavesdropper present, then that superposition pattern will go away, and there won't be any superposition pattern. So just by having a eavesdropper means any sort of detector which is finding through which slit the particles are coming, be it S1 or S2. And if we attach such a detector there, then also the superposition pattern goes away. So the idea is that the measurement collapses the superposition, and this is the Copenhagen interpretation of quantum mechanics. And based on that, this superposition pattern goes away, and this quantum mechanical superposition helps in detecting any eavesdropping that is taking place. So we'll use this in order to ensure or detect the eavesdrop. Yeah. So the second thing that we want to ensure that is there won't be any cloning of the keys that should happen, right? So for that purpose, if we encode our information in the non-orthogonal states, then no cloning theorem states that any arbitrary quantum non-orthogonal state cannot be copied using the same universal unitary quantum operation, right? So the proof is straightforward. We have considered some alpha. We have denoted unknown state as an alpha, and we want to clone it in our zero state using some operation. So the initial state is alpha 0, and what we want to ensure is we have two copies of alpha, right? So we want to copy this alpha state in the blank state, which is zero state, using some unitary operation, right? So for that purpose, in the orthogonal state, it is possible, right? If we take, we want to clone a blank state. In a blank state, it is forward. We have to apply the identity operation only. We do not have to do anything, right? And if we want to encode 1 into 0, then we have to apply the sigma z operation and it will do the purpose. Now, if you create a superposition of this 0 and 1 state with arbitrary coefficient, then you will have some problem, right? Because linearity of the quantum mechanics will not help you in this regard. So for that purpose, in equation 1, you can see that the final state is alpha a times 0, 0 plus b times 1, 1, where alpha we have taken as a 0 plus b 1. But if we take we apply this cloning in the general state, right? We want to create a copy of this alpha 0 plus b1, two copies of that. And just by multiplying it, you can find out that if a and multiplication of a and b is not equals to 0, then 1 and 2 is different. And so it is a contradictory equations, and we cannot do cloning operation for any arbitrary a and b. We have to ensure that ab is not equals to 0. We have to ensure ab is equals to 0, which will boils down to having the condition for the orthogonal states, right? So two essential features of the ideal security. One is if there is a tampering, that should be detectable, and another is that
Sorry, your voice could not be heard, sir. Sir, your voice could not be heard.
Yeah, it is having some issue. 1 minute.
Sir, in the meanwhile, questions are being posted in your Zoom chat, sir, for the questions which are coming in from the audience.
Okay.
So whenever you want to respond to the questions, you can respond whenever you want to respond.
Okay, so I take the time to respond to the question. The first question was, is quantum cryptography safer than classical cryptography? Yeah, of course. The answer is classical cryptography are only relying on the mathematical intensity. So since the iteration, since for example, if you're using a 255 number, right? It's 2 to power 255 number of combinations has to be there. So it is only on the mathematical intensity it is secure. But if you go for a quantum cryptography, we are actually the harvesting the quantum the principle, basic principle from the nature itself, and also since we are going for a single photon, so it is only intrinsic to the nature that the cryptography is designed. So it is the highest level of security is one thing. And okay, quantum resistor we have already explained, Qrngs. So post-quantum cryptographies are called quantum resistor. They are not quantum unconditional security like QKD. They cannot give, but they are given to the quantum. So the next question is, how is the quantum cryptography different from the cryptography used in Bitcoin, right? So for example, if you take any RSA or a decimal, any classical cryptography that is being used these days, this cryptography, for example, if you take RSA, right, there is a keys are being derived, right? And now if the process, we already Shakag has shown that with the stores, this can be broken if this process, if this process has been the channel can be immediately known. So somebody is trying to tamper your keys. In the classical world, it's very, very difficult to find it out. But in the quantum world, it is very easy to find it out. So that is why it offers a very, very high level of security.
Sorry, there was a connection problem from my end. So, uh, can I resume?
Yeah, sure. Please go on.
Oh, yeah. So I was in this particular slide. Yeah, so as I was discussing that using uncertainty principle in action and the no cloning theorem, I can ensure the two essential condition for the ideal security. One is if there is a tampering of the keys, it should be detectable, which is offered by the collapse of the superposition whenever there is a measurement happening. And the no cloning theorem ensures that arbitrary quantum state cannot be copied. So the random keys that we are sharing will will not be uh, copied. So these two essential features of the quantum mechanical principle helps in ensuring the security that is unconditional and that is based on the laws of quantum mechanics rather than on the mathematical hard problems. So as discussed and summarized in this particular slide, that it is impossible to make perfect copies of unknown quantum states, and this is one of the criteria to ensure the ideal security. The second is that if there is any attempt by the eavesdropper, then the information encoded will disturb the state and will expose his or her presence to the legitimate parties. And if that is the case, then the legitimate parties, after they know that there is some tampering, they will discard the key, and the secrecy of the distributed keys will be ensured. Right. So now we have discussed the principles and the stage is set for the application of quantum principles in quantum cryptography. So for that purpose, first let's discuss about the quantum random number generator, and uh, which is the essential thing to ensure in this in this arena. So before jumping directly into the quantum random number generator, let's first discuss the key features of the randomness. So in order to say that a string of the numbers is random, it should satisfy these features. First, it should be IID, which is independent, identically distributed, which any random bit taken from the string should be unpredictable. There should be uniformity of the random variables in the string. It should be unbiased. There should not be any template pattern in the key string. And in the asymptotic limit only, we can define the idea of the randomness. In the finite limit, it should hold the features that we have talked. And the basic test that you can do in your system is by compressing the file size of the file containing the key strings in order to ensure that whether it is random or not. So the any key string which does not have any pattern, or if we are claiming that it is a random key is a string, then it should not be compressible, right? So the two categories of the random number generator that are there in the market can be classified into algorithmic based RNGs and that are based on the physical process. So in the algorithmic based QRNGs, we use some some deterministic algorithm, using some random seed. We generate the final output, which passes all the randomness test. But the things boils down to that it is deterministic, because once the seed is known, then irrespective of the final output file that we have, we can predict any particular bit of that file size, right? So it boils down to the seed that we are using in order to generate the keys, or the mechanism that we are using for generating the keys. For example, if you take the irrational numbers and try to compute the
Sorry, your voice is again breaking, sir. It's not audible. Shashankaru, your voice is not audible.
Yeah. I have informed him. I think he's not in some stable. I don't know.
Sir, in the meanwhile, maybe you can.
Sure. So, hi Aryan. So he has asked about a quantum computer will need how many stable qubits? Okay, so a quantum computer requires around 8,000 logic qubits to break a RSA of 4K.
Rajesh Kaur, Shashankaru is offline. If you would like to continue, you can continue, sir.
I was discussing that there are two mechanisms or two classification of the random number possible in the literature. One is based on the mathematical algorithms that we are using in order to generate the random numbers, but the final random number is deterministic, because if the algorithm is known or if the seed is known, the essential feature is the seed, right? Once the seed is known, it is entirely deterministic feature. And there are mainly, so first is the PRNG, which is pseudo random number generator, and the second is the recently proposed PQRNG, which is pseudo quantum random number generator, where using quantum permutation or some mathematical behavior gates, people have generated random numbers, but it is not based on any physical process. That is why it is put in under algorithm based quantum random number generators. The second classification is based on the physical processes, where the universal category is the TRNG, which is the true random number generator. And under this, if the physical source is based on the classical, process, then basically it is outside the QRNG set, but it is based on the quantum phenomena. Then it is inside the set of the QRNG, under which there are multiple classification. I have highlighted two classification here. One is based on the semi-device independent mechanism, and another is based on the device independent mechanism. The distinguishing factor between the device independent and the trusted phenomena based generation of the random number is that uh, is the role played by the quantum correlation in the device independent and the SDI category. For example, in the device independent category, we have to prove the violation of some bell type inequality. And in SDI, we have to prove the violation of some steering inequality. So this is the simple classification. But any QRNG that is based on the physical process is kept under the category of the TRNG, which is a broader range of the random number generator. But we are interested in QRNG because the phenomena that is used to generate random number in the quantum picture is a simple phenomena and it is well understood, whereas using classical phenomena in the TRNG category, it is mainly the chaotic process, and we are not sure about whether it is the complexity of the phenomena that is giving rise to the generation of the random number, or it is coming out of the chaos that are responsible for the generation of the QRNG. That is why QRNG is the trustworthy category to go for. Now, in order to summarize the difference between the classical versus quantum QRNG, so the universal difference that you will find is that in the classical random number generator, there is a subjective degree of freedom which is coming into picture. For the case that we have considered, say someone is tossing the coin, then the upward thrust that the person has applied, plus the atmospheric noise parameter, plus the gravity of the planet in which this particular experiment has performed, plus some another set of parameters combined together will determine the outcome of the coin toss, right? So there are subjective degrees that are involved there. But in a quantum random number generator, it is inherent random in the sense that if you have a source of the quantum particles, which is interacting with the beam splitter, which is 50-50, then which path it will take will be determined at the instance when it is interacting with the beam splitter. Not before, not after, and not predetermined. So that's why it is called inherently random, right? So whether it will follow the path towards D0 or D1, that will be determined at the instance or at the interaction window of the quantum particle interacting with the beam splitter at that particular instance. So that's why it is said that it is inherently random and there are not a subjective degree of freedom that are involved in it. And if you used some quantum correlation that are not present in the classical world, like entanglement and you manage to show the violation of Bell inequality and cover all the side channels loopholes that could come up while the experimental implementation, then you can guarantee that the source or the phenomena that you are using for the generation of random numbers cannot come from all the classical resources combined with. And that is the power of Qrngs. Now, in the literature, there are multiple classification of the Qrngs, but here I have classified it based on the two categories. First is based on quantitative variable, under which I have classified it in DV versus CV where DV stands for discrete variable Qrng, and there are multiple approaches to generate it. For example, based on time of arrival, path based, and CVQRNGs, there are multiple approaches. Phase noise based, vacuum noise, tunnel diode based, thermal noise. There are multiple classifications. But the difference between CV and DVQRNG is in terms of the detector. For the DVQRNG, you will need a single photon detector, which is costly. But for the CVQRNG, you will need either heterodyne or homodyne detection based techniques, and which are cost effective. So in terms of cost, you will find that DVQRNG based mechanism will be cost intensive, whereas CVQRNG will be cost friendly. And under this degree of trust, classification could be based on DIQRNG, STIQRNG, and trusted QRNG as already discussed, right? Um, if the source of the random numbers is entanglement or contextuality, and you could not manage to violate the inequality, or it is based on some single qubit sources, then it comes under the trusted QRNG. But if you are working in the steering inequality framework and using the violation of the inequalities in order to have a source of randomness, then it comes under the semi-device independent regime, where by semi I means that either I'm treating the source as the black box or the detector as the black box. And under DIQRNG, if you manage to violate Bell inequality and your source of random number is coming from the violation of Bell inequality or contextuality inequality, then it comes under the DIQRNG, where you can treat both the source and the detector as untrusted parties and still have a good source of the random. But and there are multiple things like the data rate through which you can classify the QRNGs. You can classify them based on the form factors, and multiple classification can be done for the QRNG. Now, for our cases, our case that we have developed an optical QRNG where we are using a single photon source simulated using weak coherent pulses, and we are operating at the mean photon number less than 0.1. So from the plot, you can see is that the weak coherent pulses follow the Poissonian distribution. And for mu is equals to 0.1, which is mean photon number 0.1, the probability to have vacuum pulse is highest. And after that, the probability of having the single photon pulse, which corresponds to n is equals to 1, is highest, right? And if we increase the mean photon number, then this Poisson distribution shift towards the Gaussian distribution, and there the classical features will come into picture. But we want to operate in the quanta regime, so we have ensured that the mean photon number of our source is kept below 0.5. And the scheme is as follows. We have a laser source operating at 50-50 nanometer. We apply variable attenuator in order to ensure the mean photon number less than 0.1. And we have a SPD, which is operating at 30% efficiency. Then we have this time to digital converter. And then we apply post-processing using our FPGA block, and the generated random strings. We have passed all the test suits that are available, and ensure that the source is giving the random keys. So in order to judge whether the final source is indeed random or not, so there can be two kind of tests. One is for the quantumness test and another for the randomness test, right? For the quantumness test, we have ensured that the operational source is working at the quantum regime. We have performed HPT test in order to ensure that, and then for the randomness part, we have passed the recommended test suits by NIST, by FIPS, and we have passed test U01, such sort of test suits we have passed. Yeah. So this was based on the DV QRNG, but our first QRNG problem. Now, coming back to the second problem that we want to solve in the crypto world is to distribute the symmetric keys to the two legitimate parties. For that purpose, this quantum key distribution mechanism is there. So the idea is to have a transmitter, which is Alice, which is generating the qubits, which is generating single photons, and then doing the relative phase encoding and creating the qubit state preparation stage. The prepared qubits or the phase randomized vacuum V coherent pulses are then sent to the optical channel and received by the Bob. On the Bob setup, there is a decoder which contains DLI in order to distinguish between the relative phase that Alice has encoded, and based on whether the relative phase is 0 or pi, it will hit the detector D0 or D1, and based on that, Alice and Bob, after classical post processing, can ensure that they have error corrected symmetric keys at there. Now, if a smart Eve, which is Kevin, comes into picture, then what he will do? If he will try to detect the qubits, then since we are operating at beam photon number 0.1, then the phase information of typically 10 pulses is encoded in that particular photon. And if Eve managed to detect it, then the wave function collapses to particular state. And based on the key reconciliation stage, Alice and Bob will perform. And it cannot create the copies as discussed because we are operating at in non-orthogonal states, and non-arbitrary non-orthogonal states cannot occur. So it will not be helpful for Eve to snoop the system and get the keys out of it. Now, just like Qrng, we have multiple classification for the QKD. And here also we have used only two classification. One is based on quantitative variable and another is based on the quantum property. So in quantitative variable, we have DVQKD, we have CV, where DV and CV stands as previously mentioned for discrete variable and continuous variable. In discrete variable, there are multiple algorithms like DP84, DPS, coherent one-way POW kind of protocols are there. In CVQKD, we have Gaussian modulated, and here also the advantage is based on the detection. In DVQKD, we have single photon detectors, but in CVQKD, we have homodyne or heterodyne based detection mechanism, and that ensures the cost effectiveness in the CVQKD category. Now, if you take the quantum property as one of the classification features, then there are two categories. One is based on quantum indetermination, which is in research language, it is based on prepare and measure scenarios, and the classification could be BB84 and DPS, and another classification could be measurement device independent QKDs, where one can treat the measurement device as a black box. And if it is based on the quantum correlations and the degree of trust, then the classification could be semi-device independent and the DIQKD approaches, where at the end we are violating some non-classical inequality in order to ensure that we are operating in the quantum world, and the source a source of the keys is indeed quantum.
Okay. So now, uh, once we talked about the types of QKD, let's discuss what are the stages are there in the QKD. So, for that purpose, let's first consider sender, which is Alice in our QKD system. So what Alice do? Alice use Qrng in order to do the randomized space encoding and generate the or prepare the qubit states. That states are transferred through the quantum channel, which is the standard telecom fiber. At the Bob end, the Bob receives the qubits, does some decoding operation, and generates the raw keys. Now, the thing is, Alice will be sending multiple qubits, but due to channel loss, Bob will not be detecting all the qubits. So they have to do the further stages. So the first stage that will happen in the authentic classical channel, the first stage is key shifting, where Alice and Bob will ensure that they keep the qubit information pertaining to those bits that Bob has managed to detect and discard the rest. Then, because of the noise in the channel, or there could be tampering, so they have to do the error correction in order to ensure that the error in the transmitted bits is not beyond a threshold value that we can accommodate. So for that purpose, there are algorithm like bidirectional cascade-based error correction mechanism, where rather than telling out the values of the bit, what we operate at the block level and share the parity of the blocks, and then reduce the block size to half in each stage, and that's how we find the error bit value, and then we'll just correct it, but ensuring that the threshold qubit is uh, I mean threshold qubit is not achieved, is not violated. The third stage is the privacy amplification, because in the error correction will be revealing some of the information, be it in terms of parity. So we have to compress the final key size in order to ensure the security of the keys. And also, based on the attacks that we want to make our system resilient, the key length will increase, will decrease, right? So we have to apply the privacy amplification based on it. Once that is done, then the final keys that are created, ensuring that there is no eavesdropping by calculating the threshold qubit, by calculating qubit, and if it is below the threshold value, then we can ensure that the are final keys are secure. And we'll also apply the randomness test suites in order to ensure that the generated keys are random. Yeah. So from the vendor's perspective, there could be many parameters in order to optimize for creating a QKD or best QKD ever. So there could be many parameters of many choices that can decide the QKD, final QKD. So it could be the agenda. First could be whether you want to ensure a point-to-point distribution of the keys, or you want to create a network of the key distribution. There are multiple transmitter and detectors are there. So for that purpose, or if you want to break the distance barrier and ensuring that there's a trusted region, and you want to increase the distance. So two categories that we are working, we have already developed. One is based on the trusted node, and another is based on the hub and spoke, in order to ensure that we have key distribution from point to multi-point, right? So in order to create the network of the distribution. Now, it could be based on the Qrng that we have used in the QKD. It could be based on the form factor of the Qrng, and whether we want to have a Qrng that is based on device independent, or it could be based on the trusted. What is the speed, or what is the implementation mechanism of the Qrng that we are using? The third category is based on the security proofs that are available. Whether if we are operating in the quantum correlation, then the security could be guaranteed using the monogamy of the maximally incremental state, or it could be based on the uncertainty principle, based on the entropy-based security proofs, and also based on the the entanglement distillation based approaches that are derived by Shor and CRISPR. The third category that could be there is what protocol that we are using in order to implement a QKD. Because at the end of the day, we want to make it cost effective. So whether we are operating at discrete variable or continuous variable in order to ensure that the cost is reduced without compromising over the security, right? So, and the further classification or the QKD choices from the vendor's perspective would be the authentication problem insurance. Whether so we are generating or distributing keys using the quantum phenomenon, but whether we are solving the first problem, whether we are ensuring that the keys are delivered to some to authentic parties, and what protocol that we are using in order to ensure that. And finally, all these quantum principles are ensuring the unconditional security. But when we are practically implementing the QKT setup, how far the ideal principles are from the experimental implementation, and we have to find out the loopholes that are there. We have to provide the countermeasure for that. We have to ensure that each physical component that we have used is certified, is operating in the defined regime that we are working. We have to also tackle the quantum hacking or the side channel attacks that can come into picture. So all this will decide or will create a standard for the QPT that we want to achieve. Now, just to give you one example out of this QKD choice, if distance is the criteria in order to create the QKD, whether we want to break the distance. So that the estimate says that the ideal single photon sources, the distance is a function of the direct linear proportional to the transmittance loss. But practical single photon sources do not exist. So we are operating in the weak coherent sources. There, the distance is a square function of the transmittance, and this decreases the distance severely. So what we can do, we can insert a decoy pulses and increase the mean photon number of the weak coherent pulses in order to mimic the proportionality, direct proportionality to the transmittance, and this will increase the distance. Or we can use some different protocol like twin field protocol, where it has been shown that the distance is a function of the square root of the transmittance, and people have in their lab managed to achieve 830 kilometer of the distance using this superconducting based detector. And all this classification is related to the fiber-based QKD infrastructure, but one can go towards the free space or satellite-based QKD in order to achieve further large distance. But there are additional challenges. Although the loss is a bit less, but there will be scattering, there will be beam broadening, there will be detector manufacturer challenges and all. But yeah, so this we have already discussed, but just to give you an idea, in our setup, the scheme that we are using is the distributed phase reference QPD. Already talked about the randomized phase encoding that we want to build. The key rate that we managed to achieve is 25 to 35 kbps at 40 kilometer range. It depends upon the operating conditions, so that will decide the upper and lower bound. And as we increase the distance, the key rate is decreasing, but it's still in 100 kilometer setup also we managed to achieve close to 2 kbps. And Qber value is less than 5%. we have applied 25 to 50% of the privacy amplification in order to ensure that final keys are the same. Yeah, so that's it from my end. If you have any questions, we can address those questions.
Sir, I believe few of the questions are already there in your chat.
Yeah. So in order to so book typical book I cannot recommend, but you can go through the review papers. Very good review papers are there for the quantum cryptography. This is an answer to Vignesh from Stanipuri, Hyderabad, and then the RN from Mushirabad has asked a quantum computer will need how many stable qubits to be cryptographically relevant. So stable qubit is one thing, but the thing is that we were talking about was the logical qubits. So the current quantum computers, which is in the NISQ era, they have they are noisy, right? So whatever computation you perform, you have to do error correction, rigorous error correction in order to ensure that the results that you are getting is correct. And they are designed for some specific problems. So the theoretical estimates that we have talked in the starting few slides says that RSA 4096 will need somewhere around 8,000 qubits in order to factorize the number, and the estimated time was 255 hours. So these are theoretical estimates. So uh, cannot comment upon the current computers. So once we have a large scale logical system, all these theoretical estimates are valid for that purpose. What can quantum cryptography be used for? So like we discussed, in order to ensure the ideal security, two essential features are there. First, the keys should be truly random. And the second thing is we want to distribute the symmetric keys among the legitimate users, right? So quantum cryptography can be used for solving these two purposes. What hurdles do researchers face in developing a quantum computer? So I'm not from that particular background, but based on my analysis, or there are multiple approaches to build a quantum computer, right? The 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 basic thing is to ensure the operating temperature, because the superconducting based quantum computers approaches need the cryogenic temperature, and in order to maintain the coherence time of the qubits that you are creating. And then further challenges are the interaction with the environmental noises that are there. Then as you increase the number of qubits, then ensuring that they are performing the uh, intended operation for the long duration of the time. So, and then this was about the logical qubit. There are other, this was about the superconducting qubits. Other approaches like photonic based quantum computer, NMR based quantum computer, they have other challenges. But the best approach that I liked was based on the topological qubit based quantum computers, because there from the starting, the idea is to ensure that the qubits perform the logical operation and they are confined in the created topology. And so there is no space for having the uh, error that is coming into picture, and it is also scalable. So these are few of the challenges. Then Teja from Gachibowli, Hyderabad, please clarify what types of job opportunities will be available to those who take this quantum computing. So this was more into quantum cryptography. So both these fields will go hand in hand, right? The advancement in quantum computing will create opportunities in quantum cryptography, and uh, at the end of the day, we have to ensure the security of the messages that are going. So there are opportunities both in the theoretical as well as in the experimental field. In the experimental field, the challenging problems are the good single photon sources and the detectors. Other components are fine, but when we are trying to implement, then what sort of side channel attacks that can come into picture, one has to rigorously thought about it. In the quantum computer, if you like doing theory, then you can learn about the quantum machine learning. You can solve the existing problem, and there are many algorithms in the NISQ era that are found to be useful in order to solve a problem that the classical computer will not match. So you can dig deeper into such sort of algorithms that can work in the NISQ era and still give you quantum advantage. I think we have addressed all the questions.
TSAT team ఇంకేదైనా క్వశ్చన్స్ వచ్చాయా? హలో TSAT team.
Okay, question. Are these courses helpful for those who does not have programming or tech background and really want to focus on development of application of quantum computing? Okay, so see, if you want to develop something like a quantum computing or a quantum communication thing, right? It is not only one department, right? It is an inter-department work which is giving ways to this kind of a setup. If you see some photonics, somebody from the photonics physics background is required, somebody from a theoretical backgrounds are required, somebody on the informational security backgrounds are required, somebody from the electronics are required, somebody from the mechanical is required, somebody from the ITs are required. So all these levels of communications, so even in our quantum cryptography, all these departments should be there. Then only the success of all this department put together and solving a problem is what we are trying to see. So it is not just one thing. Programming is one aspect of it, but there are a lot more things out there like informative theoretical. You have to prove the informative theoretical. There are some experimentations which will help in making the use using the photonics things. If there are some experimentation mechanicals also, because as Shashank was explaining, right? There is a you have to maintain the temperature. Even in our QKD, right? We have to maintain a temperature of minus 40 degree for the single photon detector. So that kind of, so how to enclose, how to make this one, that is also is very, very important.
TSAT team ఏదైనా క్వశ్చన్స్ ఇంకా వచ్చాయా? As well as even your colleague, even Shashank Garu also, for enlightening our students on quantum cryptography and making our students aware of quantum computing. Though it's relatively new course for the students, but still the students are showing enthusiasm in learning the course. Thanks a lot for your contributions, sir.
Yeah, it was a pleasure for us also to share with you. So yeah. So if you guys visit Bangalore, please visit the. Hello. Hello.
Yes, sir. Yes, sir. Yes, I could go on.
Yeah. So it was a pleasure also from our side to share the topics. And also, if you want to learn more or if you want to see the quantum system, you can fix up some time. You can come down to Bangalore actually to see how the real QKD systems are in action. So that also we can organize if you guys are very excited about it.
Sure, sir. I think the students will surely utilize this opportunity of coming down to your office one day and seeing what real quantum computing really looks like.
Yeah. So we don't have a quantum computing device. We have a quantum cryptography device. So we have a QKD and Qrng. So how that is action is working in the lab, how it is being made, all these things they can learn.
Sure, sir. Sure. Thanks a lot. Thanks a lot for your session, sir.
Thank you. Have a great day. Bye-bye.
Bye, sir.
ఉపాధ్యాయ వృత్తిపై ఆసక్తి ఉందా? పని చేస్తే ప్రభుత్వ ఉపాధ్యాయుడిగానే పనిచేయాలనుకుంటున్నారా? తెలంగాణలోని ప్రభుత్వ పాఠశాలల్లో పని